Hello everybody, today I'm here to discuss about vehicle license plate recognition through video capture. This is my final project as part of pattern recognition course at University of Florida with the ECE department. So the presentation outline is here. Introduction to vehicle license plate recognition application, ideal vehicle license plate recognition system characteristics, applications of the vehicle license plate recognition, VLPR architecture, algorithms for VLPR implementation, experimental setup, results, and conclusion. Introduction to VLPR application. Vehicle license plate recognition is one of the prime computer vision applications used by intelligent transportation system for license plate recognition. It is a real-time application to quickly and successfully process license plates under different environmental and geographical conditions. Computer vision, image processing, and pattern recognition algorithms are applied for designing an efficient vehicle license plate recognition system. The various challenges like viewing angle, shutter speed, and camera resolution should be handled very carefully while designing a vehicle license plate recognition interface. An ideal VLPR system characteristics are seen below. In a VLPR system, very high license plate recognition accuracy is required, fast processing speed, and the ability to handle wide range of license plate with different plate variations like size, plate colors and font, and standard and customized plates and inclination and occlusion should be considered. And VLPR system should be tolerant to imaging variations like illumination, background noise, camera resolution, camera shutter speed, motion blur, viewing angle, and number of cameras. So these are the ideal characteristics of a VLPR system. So some of the applications for a VLPR system are vehicle theft prevention, automatic toll road collection, security zone access control, traffic monitoring and control, state border control, vehicle speed monitoring and police law enforcement, statistical analysis, and there are many more real-time applications of vehicle license plate recognition systems. So here we would see the architecture of the VLPR system implemented in our application through video. So we are reading a video, read video frame, and then license plate extraction is done. After the license plate extraction, license plate autocorrection, that is segmentation and alignment is done in the autocorrection action, and finally license plate recognition is done through template matching and character recognition. So the input video file is read and a single frame image is extracted from it. From the sequences of images extracted from the input video, the desired input image is selected and further processed to detect and extract the license plate, followed by character recognition and template matching for license plate recognition. So in the license plate extraction action step, various feature extraction algorithms are implemented. Some of the feature recognition algorithms are discussed here, which are used in our application. So edge and boundary information extraction. So the edge and boundary information extraction works based on the brightness change in the license plate region that is more remarkable and more frequent. Regions with high edge magnitude and high edge variance are identified as possible license plate regions. It is the main advantage of this feature extraction is it is simple and fast to implement, and though it has a drawback of being not very efficient with complex images, but it is very robust to noise, and a Sobel filter is used for this kind of edge detection. In an application, we use a Sobel filter for vertical and horizontal edge detection. Hue transform detects straight lines, that is boundary based extraction. We also use hue transform for template alignment, that is license plate alignment in our application. Texture feature extraction. License plates have high contrast of colors between background and characters, and this is known as the texture feature of the license plate. A Gabor filter is used for texture feature extraction. This filtering is applied to all the three RGB channels, and thus single color edges are filtered out. It has the advantage of analyzing texture in an unlimited number of directions and scales. The disadvantage is that it is computationally expensive and slow for images with large analysis. Geometric feature extraction. Geometric features include rectangle height, width, area, aspect ratio, the number of rectangles included in another rectangle, etc. So the license plate 8 rectangles are detected by using efficient geometric attributes to locate lines that form the rectangles, and simple geometric features like the aspect ratio is used as a metric. Aspect ratio is the ratio of width and length of a license plate rectangle. Another feature extraction algorithm which is implemented in our license plate is block-based extraction and bounding box. So block-based methods consider blocks to be possible license plate regions. High edge magnitude is Q for such block-based extraction. The advantage of this method is that it works well with license plates whose boundaries are not clear because block processing is independent of the edges of license plate boundary. License plate alignment. So once we get the license plate, once the license plate is detected and extracted, it is then we do the license plate alignment. The license plate alignment focuses on optimizing the boundaries of the detection window to ensure that the colors on both the sides of the boundaries are most different. Statistical histograms are computed and color difference between various regions is measured. The positions of lines where a maximum difference is achieved will form the aligned result rectangle, which is an accurate license plate region. Template matching. Template matching is done after the license plate is extracted and aligned. Template matching involves measuring the distance or similarity between the template and the character. Whichever template the character is similar to, the corresponding index will be the recognition result. Binary image is commonly used in template matching because if a grayscale image is used, it will change if the lighting is different. And this kind of method is useful in recognizing characters that are single font, non-rotated, non-broken, and fixed size. After some of the other feature extraction algorithms which can be implemented for license plate extraction are scale invariant feature transform. Scale invariant feature transform is a technique to obtain robust local key points on an image which is invariant to scale, rotation, and affine transformations. The main idea here is that by constructing a pyramid of Gaussian blurred versions of the image, the local extrema point that exists in the entire Gaussian pyramid can be obtained. These points turn out to be stable even when the images are subjected to various possible transformations. This feature detection technique consumes more time and requires high quality images. Another feature extraction algorithm which can be implemented for license plate recognition is maximally stable extremal regions. Maximally stable extremal regions is a technique to extract regions for classification. The key idea here is if that image is being transferred into a binary image with a range of thresholds, a set of regions emerge. By tracking the region's transformation from one threshold to the next, observation is made that the regions grow in size until at some point the regions merge with another region. So the region before the merging is called as an extremal region, and an extremal region that spans a large enough of the threshold range is referred to be as maximally stable. These are the regions that are stable even when the image is subjected to various possible transformations, especially the affine transformations. Sobel filter. A Sobel filter is used for edge detection, and we will see how exactly a Sobel filter works. A Sobel operator performs two-dimensional spatial gradient measurement on an image to emphasize the regions of high spatial frequency that correspond to the edges. It is used to find the approximate absolute gradient magnitude at each point in an input grayscale image. Transferring a 2D pixel array into statistically uncorrelated dataset enhances the removal of redundant data. Thus, there is a reduction of the amount of data required to represent a digital image. A vertical Sobel operator is used to detect the vertical edges, as the plate area contains rich edges information. The vehicle image is convolved with vertical Sobel operator to get the vertical gradient image. Then the mean of the absolute gradient values in the vertical gradient image is computed and multiplied with threshold gradient coefficient. The binary vertical edge image is obtained using this threshold. Although Sobel operator is slow to compute, the larger convolution kernel evens the input image to a great extent and thus makes the operator less sensitive to noise. Hue transform. Hue transform is a technique which can be used to isolate features of a particular shape within an image. The transform is implemented by quantizing a hue parameter space into finite intervals. As the algorithm runs, the coordinates of the point of edge segments known through edge detection algorithm are transformed into a discretized curve and accumulated and the accumulator cells along the curve are incremented. So it is basically like once the points are known, the line is formed through with the help of the points. So here the points correspond to the edges detected through the edge detection algorithm, and hue transform is detecting of the line through the points which are previously detected. The resulting peaks in the accumulator array represent the strong evidence that a corresponding straight line exists in an image. Hue transform. Thus, hue transform is used to identify parameters of a curve which best fits a set of given edge points. The edge detector defines only the location of features in an image. So, the main advantage of hue transform is here. It also tells us what are the features and how many features exist in an image. Advantages of using hue transform are: it deals well with non-locality and occlusion, detects multiple instances of a model in a single pass, and is robust to noise. Challenges of hue transform are complexity of search time, increases exponentially with the number of model parameters, non-target shapes can produce spurious peaks in parameter space, and hard to pick a good grid size. So next, let's see about morphological image processing. Morphological image processing applications take a binary image and a structural element as input and combines them using a set operator like an intersection, union, inclusion, and complement. The objects in the input image are processed based on the characteristics of its shape, which are encoded in the structuring element. The structuring element is size 3x3 matrix, and it has its origin in the center pixel. It is shifted over the image, and at each pixel of the image, its elements are compared with the set of underlying pixels. If the two sets of elements match the condition defined by the set operator, then the pixel underneath the origin of the structuring element is set to a predefined value of either 0 or 1 of the binary images. Morphological image processing can be further classified into image dilation, wherein we grow the image regions, and image erosion, to shrink the image regions, image opening, structured removal of image region boundary pixels, image closing, structured filling of image region boundary pixels, hit and miss transform, wherein an image pattern hatching and marking, image thinning. This is method where a structured erosion using image pattern matching, image thickening, structured dilation using image pattern matching. We used image dilation and image thinning algorithms in our application. Experimental setup, license plate detection and extraction. So the input video used in the application consists of a total of 142 frames, and a single frame is selected to capture the image. Captured image is converted into a grayscale image, and a Sobel filter is applied on the grayscale image for vertical edge detection on the vertical edge detection. Here we see the input image captured through the video, and a vertical edge detected image through the Sobel filter. After the Sobel filter is applied, a Gaussian filter is then applied to blur the image and find the high density area in the vertical edge map of the input image. Gaussian smoothing operator is a 2D convolution operator that is used to blur the images and remove noise. It uses a kernel that represents the shape of the Gaussian bell-shaped hump. Gaussian distribution is non-zero everywhere, which requires an infinitely large convolution kernel, but it is effectively zero more than about 3 standard deviations, so that the kernel can be truncated after 3 standard deviations of the Gaussian distribution. In the experimental setup, the license plate used to have a high contrast of colors between the background and the characters. So a Gable filter is used for texture feature extraction. Here we can see high density Gaussian filtered image, and here we can see color feature extraction image through a Gabor filter. And the ratio of region area versus rectangular bounding box area is used to filter out arc shaped regions by threshold. A fixed aspect ratio of 2:1 with a small variation to select possible regions of license plate. Once the license plate is detected, it is highlighted with a yellow box arcs in the origin image, and it is labeled. So here we see the highlighted license plate, undetected license plate is shown here, and this is the plate 1 and this is the plate 2. We will see the further experimental setup and results in the next video.